Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 5th, 2026, just yesterday. It introduces the first systematic reinforcement learning framework, specifically designed for visual autoregressive models, which resolves training instability and boosts text rendering accuracy by over 40%. The paper is titled VAR Done Right, Tackling Asynchronous Policy Conflicts in Visual Autoregressive Generation. And as we'll see later, the method achieves state-of-the-art results that actually surpass strong diffusion-based baselines. Figure 1 illustrates the root cause of these stability issues by comparing the token dynamics of different generative models. If you look at the middle and right panels, standard autoregressive and diffusion models maintain a constant input size throughout generation, resulting in a flat, predictable line. In contrast, the left panel reveals the unique challenge of the visual autoregressive approach. Here, the number of query tokens grows exponentially as the model progresses from coarse outlines to fine details, creating severe policy conflicts. Well, Figure 2 plots the training reward over time, illustrating the direct impact of that instability. The gray line at the bottom tracks the vanilla group relative policy optimization baseline, which clearly struggles to improve. In fact, after about 150 steps, its performance destabilizes and actually begins to decline. By comparison, the colored lines above show the proposed method using value as middle return. Whether using a prefix of 128 or 256, these partial scale updates allow the model to learn steadily, reaching significantly higher reward values without the collapse seen in the baseline. Alright, Figure 3 details the solution, which the authors call value as middle return. The diagram visualizes the two-stage pipeline, where the optimization is split at a middle time step, M. In the top branch, the prefix policy generates the initial course structure, receiving an intermediate reward estimated via Monte Carlo sampling. Then, the bottom branch handles the suffix, refining the details to complete the generation. By decoupling these stages, the framework isolates the optimization effects, preventing the high-resolution later steps from destabilizing the foundation laid by the early steps. So, while Figure 3 addressed temporal issues, Figure 4 illustrates the spatial solution, known as mask propagation. This diagram maps how the algorithm assigns credit across the model's multi-scale hierarchy. The process actually works in reverse. It starts at the finest resolution on the right, labeled R5, identifying which tokens determine the final reward. It then projects that focus, shown as the red highlighted regions, backward to the coarser scales on the left. This ensures that gradients update only the causally relevant parts of the image structure, effectively filtering out noise. Figure 5 puts these methods to the test with visual comparisons of text rendering. In each of these 8 pairs, the left image shows the output before optimization, and the right shows the result after reinforcement learning. A clear example is the sticky note in the bottom right corner. Notice how the baseline hallucinates extra words, writing done right, while the optimized version cleanly generates the correct title. Similarly, in the phishing scene above it, the model corrects a stuttering caption from "God gotcha" to simply "gotcha," proving its ability to fix fine-grained text errors. Okay, Table 1 now quantifies those improvements on the CVT-G2K dataset. If we focus on the bottom 2 rows, we see the direct impact of the reinforcement learning stage. The base NextFlow model starts with a word accuracy of roughly 0.55. But NextFlow RL jumps to over 0.78. That is a massive 41% relative increase. Crucially, this score outperforms strong competitors like TextCrafter and SD 3.5 Large, shown in the middle section, and achieves the highest clip score in the entire table. To wrap things up, the key insight here is that standard reinforcement learning fails on visual autoregressive models due to their shifting input sizes. By explicitly managing these conflicts, this research proves that autoregressive generation can actually surpass dominant diffusion baselines in complex tasks like text rendering. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.